Good morning. Hope everybody's doing all right this morning. So we are going to start with section 3.4 today. So this is limits at infinity and horizontal asymptotes. This is pretty much like the last thing that we need in terms of graphing some of these functions now. So then after this, we'll look at another section where we kind of put everything together that we've talked about in this unit. And then there's only one other section after that where we look at some optimization problems using some of these strategies now. Okay, so those will be like the real world problems using these as applications. All right, don't forget the next homework right now I have set to be due Thursday at midnight. So as we get through this section and possibly into section 3.5 today, you should be able to get a start on that one. Don't forget, though, that the homework on 3.1 to 3.3 is due by midnight tonight if you haven't already finished that one. And again, the test most likely will be early next week is what I'm looking at, because I think we should be able to finish up this unit either Thursday or Monday is what I think right now. Then we'll have a review, half day in there, and then the test will be posted. So probably early next week, Monday is when the test will be posted, which means it'll probably be due on Wednesday of next week. Okay. But again, all that's subject to change depending on how long it takes to get through these sections. But that's what you can plan on for right now. Okay. Any questions, comments, concerns before we get started on section 3.4? All right. So like I said, we're going to look at limits at infinity now. So we're going back to some limits now, and then how those are related to our horizontal asymptotes for our graphs. So we're going to let f be our function defined on some interval from a to infinity, right? So we're just looking out towards positive infinity right now. The limit as x approaches infinity of our function is equal to L means that the values of f of x can be made arbitrarily close to that value by requiring x to be sufficiently large. In other words, as we go out towards positive infinity, we are approaching some specific value. Okay, and you can see that on the three graphs below here. These are kind of the three scenarios that might happen. Either we could be approaching from the bottom, right? We have that line, horizontal line at y equals L there. And so as we go out towards positive infinity, our function is getting sufficiently close to that L value. Or it could be approaching from above, like the second graph, right? But again, as we go out towards infinity, we're still approaching that same L value. Or we could get something that looks like the third graph here, where it's actually oscillating, okay, but those oscillations get smaller and smaller and smaller, and so it's still approaching and tapering towards that L value. Okay, so in all three of these cases now, we would say the limit as x approaches infinity is equal to that L value. All right, now we could also look towards negative infinity. Okay, and now it's basically the same thing. We're just saying as we go out towards the left, we're defined from negative infinity to a. Okay, and it's going to be the same thing. We're approaching some L value as we go out towards negative infinity instead. Okay, now in either of those cases, we would call the line y equals L a horizontal asymptote. Okay, so just like we have vertical asymptotes where we can look at limits that are equal to infinity and negative infinity, now as we go out towards infinity or negative infinity in the x direction, if we're approaching a specific y value in either direction, we would call that a horizontal asymptote. Now, don't assume that your horizontal asymptote has to be the same on the left and the right. In some cases, you'll have one on the right and not on the left. Sometimes you'll have one on the left and not on the right. Sometimes you could have one in both directions, but they're different values. And then sometimes they will be the same horizontal asymptote on both sides, okay? So we do have to check both directions because they could be different in each direction now. That's exactly what we're going to be doing, is looking at our limits as x approaches infinity, limit as x approaches negative infinity, and if we're approaching a specific value in either direction or both directions, then we're going to have horizontal asymptotes for that graph. All right, so let's take a look here. This time we're just given the functions graph. We want to find limits at infinity, infinite limits, and any asymptotes. Okay, so when it asks for infinite limits, we're just asking, are there any places where the limit is equal to infinity or negative infinity? Then we're going to look at our actual limits at infinity and negative infinity, and then we'll discuss the asymptotes based off of those. So let's start with infinite limits. Are there any places on this graph where the limit itself is approaching either infinity or negative infinity? Okay, good. So at -1, right? So here's -1 right here. Notice as we go up towards that value, it's actually approaching positive infinity. So we would say the limit as x approaches -1 of our function f, that's going to be equal to positive infinity. Any questions about that one? Okay. Do we have any other locations on our graph where the graph is either approaching infinity or negative infinity? At 2, right? Now notice here at 2, on one side it's approaching infinity, on the other side it's approaching negative infinity. So we are going to have to split up this limit from the left and the right. So we'll say the limit as x approaches positive 2 from the right. What's it going to be from the right-hand side, positive or negative infinity? That one's going to be positive, right? So this is approaching positive infinity, and that means our limit as x approaches 2 from the left, that side is going towards negative infinity instead. Right. Any questions about those limits? Okay, now, based off of that, what type of asymptotes are we going to have at those locations? Vertical, right? So at each of those places on our graph now, this tells us we're going to have vertical asymptotes at x equals -1 and x equals positive 2. Okay, so just remember, anytime you have a limit that's approaching infinity or negative infinity, that tells us where our vertical asymptotes are. All right, now let's look at our limits at infinity and negative infinity. So now we're actually taking the limit as x approaches infinity of our function. Okay, so as we approach positive infinity, are we approaching a specific value on our graph now? Good, right? So if you look on our graph here, this line right here would be 4. And you can see as we go out towards positive infinity, it's getting closer to that horizontal line right there. So we would say that that limit as we approach positive infinity is equal to 4. Any questions about that limit? Okay, now we want to look at the limit as x approaches negative infinity instead. Okay, and as we go towards negative infinity, good, we're approaching this value right here, that's 2. So the limit as x approaches negative infinity is going to be equal to 2. Any questions on that limit? Okay, now, based off of those limits, what does that tell us about our graph then? So what are we going to have at those locations? Horizontal asymptotes, good. All right, so this tells us where our horizontal asymptotes are. So one of them is at y equals 4, the other is at y equals 2. And be sure when you're listing out asymptotes in general, right? Vertical asymptotes are lines, so they are x equals some numerical value. Horizontal asymptotes, same thing, they are horizontal lines. So it has to be y equals whatever the numerical value is. Any questions on finding those limits or how they're related to the asymptotes now? And just to make sure it's clear, right, even though this line, right, at 2, if I extend it, it's eventually going to cross over the function. Same thing with the one at 4, right? If I extend it, it's eventually going to cross over the function. All we care about, though, for horizontal asymptotes is what's happening at infinity and negative infinity. And if we're approaching a specific value at those places, then we still call it a horizontal asymptote, okay? So it does not matter what's happening in the middle of your graph here. All right, so now we want to find the limit as x approaches infinity of 1 over x and the limit as x approaches negative infinity for 1 over x. All right, now, how do you want to do these limits? So if we want to think about the limit as x approaches infinity of 1 over x, how would we do that? So how do we do limits in general, right? So if you think back to when we first started looking at limits, if we wanted to know the limit as x approached some value, what did we do? Okay, so when you say the denominator, what do you mean by that? Okay, we substituted values in there, right? So, if we were saying what's the limit as x approaches 2, well, we could actually put in, 2.5, 2.4, 2.3, 2.2, right? And see what value we're getting closer to as we do that. Well, in this case, we're trying to approach infinity. So what values might we want to substitute in there to see what this limit is approaching? So if we wanted to make a table of values and you wanted to think about the limit as x goes towards infinity, what values would you substitute into your function? Okay, big numbers, right? All right, so that's fine. We'll start with 99, right, if you want to do that. So if we plug in 99 here, we're going to get 1 over 99. Let's get a decimal approximation of that just so we can kind of get an idea of what's happening here. So 1 over 99 is going to give me 0.01 with a repeating 01. Okay. Now, one value is not enough, right? So what value would you want to test next? Okay, we'll go with 999, right? Because we're trying to approach infinity. We want to make these larger. So now if we do 1 over 999, what's that going to give us? Okay, good. So 0.001, where that repeats, right? All right. What's another value we could test now? All right, 9,999. Just so you know, right, it doesn't have to be nines, right? We could have tested 100, 1,000, 10,000, right? Whatever you want to do there. Okay, but if we do this now, that should give us 0.0001, where those 4 decimals repeat now. All right, now hopefully you can kind of see a pattern here, what's emerging. So as we continue to make these values larger and larger, what does it look like that f of x value is approaching? 0, right? Okay, so that decimal is getting smaller and smaller and smaller. It's never going to become negative, right? It's always going to stay positive. Okay, so as we approach infinity, that limit is approaching 0 now. Any questions about that one? Okay, now we want to do the same thing with negative infinity. So we're looking for our limit. X approaches negative infinity of our function. Okay, this is 1 over x. So if we do this one now, again, I'm going to create a table of values. Okay, so what value would you want to start with this time? Okay, good. So we just need to make sure it's negative because we're going in the negative direction towards negative infinity, right? So if we do 1 over negative 99, in this case, it's going to be the same decimal, only negative, right? So it's going to be negative 0.01, repeating. All right, what value do you want to test next? Okay, negative 999. Keep it consistent with what we had over there. So again, same decimal, only negative, so negative 0.001, repeating. And if we go with negative 9,999, and it's going to be a negative 0.0001, repeating. All right, so again, hopefully you can kind of see the pattern at this point. What value is that approaching then? Still approaching 0, right? Because these decimals, even though they're all negative now, okay, they're approaching 0 from the negative direction, so that limit is still going towards 0. Any questions about that one? Now, what does that tell us then about our graph of the function 1 over x? Good. There's going to be a horizontal asymptote on this graph at y equals 0. And if you remember what the graph of 1 over x looks like, okay, this graph actually looks like this. We have this piece down here in the third quadrant, and then we have this piece up here in the first quadrant. Vertical asymptote at 0, right? Because we can't have 0 in the denominator. But then we also have a horizontal asymptote along the x-axis at y equals 0 in both directions, right? And notice as we go towards positive infinity, it's approaching 0 from the top. That's how we got those positive values. And then as we go towards negative infinity, we're actually approaching 0 from the bottom, which is why we get all those negative decimals as we go towards negative infinity here. But the asymptote is the same in this case on the left-hand side and the right-hand side. Any questions on that now? All right. Now, if r is greater than 0 and is a rational number, then the limit as x approaches infinity of 1 over x to the r power will always be equal to 0. Okay, so it doesn't matter what that exponent is as long as it's some rational value, right? Rational means fractional, right? So it could be 2, 3, 4. It could be 1/2, 1/3, 1/4. Does not matter. 1 over x to some power like that will always be equal to 0. And the same thing as we go towards negative infinity, limit as x approaches negative infinity of 1 over x to the r, where r is some rational value. And as long as r is positive, okay, then we know that limit's always going to be equal to 0. Okay, so no negative exponents, okay, only positive exponents. But as long as you can write that exponent as a fraction, okay, then it's always going to be equal to 0 in this case. All right, so now we want to evaluate a limit. We have a rational function here, 3x squared minus x minus 2 over 5x squared plus 4x plus 1. We're going to use our limit rules that we already know to try to evaluate this limit now. Okay. So notice, infinity is not an actual number. We can't do a direct substitution. So we are going to have to break this thing down and think about how we can use our limit laws to actually figure out what this limit's going to be equal to. Right, now, the first thing we're going to always do with a problem like this, we're going to identify what is the degree of the denominator. So what would be the degree of the denominator of this function? 2. Good. Right. So we're looking at this x squared term right here. So what I want to do now is I want to actually divide every single term in my function by x squared. Okay, so I'm just going to go through. I'm going to keep my limit as is. We're still taking the limit as x approaches infinity. But I'm going to divide every single term by x squared now. We're going to have 3x squared divided by x squared minus x divided by x squared minus 2 over x squared. And then same thing in the denominator, 5x squared over x squared plus 4x over x squared plus 1 over x squared. Okay. So figure out what your degree is, right? And whatever that variable is, we're going to divide every single term by that power now. And this works for limits as we approach infinity or negative infinity. Okay, in both cases, we're going to do the same thing. Now we're going to simplify. Okay, so again, we're still looking at our limit as x approaches infinity. If I simplify my numerator now, what's 3x squared over x squared going to give us? Just 3, right? The x squares cancel out, so now we get a 3. Minus, what's x over x squared going to give us? Good, 1 over x, right? Because one of those x's cancels out. Minus 2 over x squared. We cannot simplify at all. There's no x's to cancel out, so this is just going to be 2 over x squared. Now let's look at the denominator. 5x over x squared is going to be what? That's going to give us a 5. Good. Plus 4x over x squared. Going to be 4 over x. Again, one of those x's cancels out. And then 1 over x squared we can't simplify, so that's going to be 1 over x squared. All right, now remember, we have our laws of limits where we can actually split up addition, subtraction, multiplication, and division, right, into separate limits. So that's basically what we're going to do now, is we're going to take the limit of each one of these terms. Well, I'm not going to actually write it out as taking the limit of each one of these terms, okay, but let's go through and take it. If we do the limit as x approaches infinity of 3, what is that limit going to give us? What's the limit as x approaches? Exactly, it's 3. It's the constant, right? Anytime you take a limit of a constant term, it doesn't matter what x is approaching, you're going to get the constant. So that first term is just going to give us a 3 now. Minus. What's the limit as x approaches infinity of 1 over x? 0, right? That's the one we just did. Okay, so that's going to give us 0 minus. Now, the limit as x approaches infinity of 2 over x squared, remember we said that if it's x to some rational power, that limit should always be what? 0, right? And it doesn't matter that we have a 2 in the numerator here, okay, because that denominator is, growing exponentially in this case. Okay, so this is still going to be approaching 0, no matter what that numerator is, as long as there's no variable there, right? If it's just a number. Okay, now let's look at our denominator. Limit as x approaches infinity of 5 is going to give us what? 5. Good. Plus limit as x approaches infinity of 4 over x. 0 again, right? So again, even though there's a 4 in the numerator, doesn't matter. We have the x in the denominator. That's approaching 0. And then the limit as x approaches infinity of 1 over x squared, also 0. Now we simplify. So what is this going to simplify to? 3/5. Perfect. So now we know our limit as x approaches infinity of that rational function is just going to be 3/5. But again, the steps here, you always want to divide by the highest exponent in your denominator every single term, simplify that, and then we can go term by term and think about those limits individually. Now, if you remember back to Math 171 pre-cal, we have rules for horizontal asymptotes, right, that you probably learned back then, and you probably didn't understand why they even worked. This is why they work, okay? So if you remember, if the degree in the numerator and denominator are the same, and you want to find a horizontal asymptote, what can we do? So what's the shortcut for finding the horizontal asymptote if the degree on top and bottom are the same? Yeah, just look at your coefficients in front and divide them, right? So we're basically just taking the 3 from here and the 5 from here, dividing them, we get 3 over 5, and that's our limit, okay? Because that is where the horizontal asymptote is going to be. This tells us there's going to be a horizontal asymptote at y equals 3/5 now. Again, that only works if the degree on top and bottom are the same. Then we had a rule that said if the degree on the top is bigger than the degree on the bottom, okay, then that's always going to give us no horizontal asymptote. And then if we have a degree bigger on the bottom than the top, then it's going to always be y equals 0. Okay. Yes, okay, so Jairo, in this case, if we were approaching negative infinity, this one would give us the same thing. Okay, we would still go through the same process, and this one in particular would still give us 3 over 5. Okay, now, again, that won't always be the case, right? The steps will still be the same, but just be very careful because you're not guaranteed to get the same limit on both sides, okay? So there will be times where, based off of what we divide by, that limit as we go towards negative infinity might actually give us a different value than what we got for positive infinity. Any questions on this one now? Yeah, right. The one with the graph where each side went towards different numbers, right? Okay, so that is a possibility. In general, with your rational functions like this, those limits should work out the same on the left and the right. It's when you start putting other things like square roots and things like that in there, that's when you have to be really careful because the positive infinity and the negative infinity could give you different values in those cases, okay? Any other questions here? All right. So now we want to find horizontal and vertical asymptotes of this graph now. So notice we're looking for horizontal, which is what we've been doing, right? Those limits at infinity and negative infinity. This time we also want to find vertical, though. So which one do you want to start with, horizontal or vertical? All right, let's do our vertical then. So if we do our vertical asymptotes, whenever you've got a fraction here, how are we going to find vertical asymptotes? Okay, so take the denominator and do what with it? Set it equal to 0. Good. Because we know we can't have 0 in the denominator. So wherever the denominator is equal to 0, that's going to give us a vertical asymptote. We're just going to say 3x minus 5 equals 0. Now we're going to solve that, right? So we'll add 5, divide by 3. So x equals 5/3. There's our vertical asymptote. And there will be cases where you have multiple vertical asymptotes, right? If your denominator had more terms and you could factor things like that, then you just set each factor equal to 0 and you get multiple vertical asymptotes in those cases. Any questions about finding the vertical asymptote here? All right. Now, how are we going to find horizontal asymptotes? Okay, good. We've got to do our limit as we approach infinity and our limit as x approaches negative infinity, right? So we have to do both. Let's start with the limit as x approaches positive infinity. So our function this time, we've got square root 2x squared plus 1 over 3x minus 5. All right, so again, infinity is not a number. We can't direct substitute in this case. So we're going to do the same thing that we did on the previous problem. So if we look at our denominator this time, what are we going to end up dividing by? X to the first power. Perfect. Okay, so here's what I'm going to do. I'm going to take my limit as x approaches infinity. In my numerator now, I have the square root of 2x squared plus 1. I'm going to divide all of that by x. Then I'm going to come to the denominator, divide each of our terms down here. So 3x over x minus 5 over x. Now, I need a way to be able to actually simplify that fraction in the numerator by dividing each of the terms inside the square root. If I move that x into the square root, what is it going to become? So not x cubed. Think about this. So if I take limit x approaches infinity, I basically want to get one big square root now where that x gets moved into the square root so that I can divide each of my terms inside the square root by that, whatever that term is. So if it's an x on the outside, not x to the 1/2, right? Because we're not taking the square root of that x, right? Right now it is an x. What would I have had to take the square root of to end up with an x on the outside? So what would it need to be on the inside so that once I take the square root, it gives me an x on the outside? In other words, the square root of what is equal to x? x squared, right? So I need an x squared inside the square root so that once I take that square root, it gives me the x on the outside that I want. So now this is going to become 2x squared over x squared plus 1 over x squared. So anytime you move that x into the square root like that so that you can divide each term by it, it's just going to become an x squared instead. Any questions about that step? All right, now let's simplify the denominator here. So 3x over x is going to give us what? 3, good. 5 over x we can't simplify, so that's still just minus 5 over x. All right, now let's clean up the numerator, right? Because now I can actually divide each of those terms. So we're going to get limit x approaches infinity. Up top now, 2x squared over x squared is going to give us what inside of our square root? 2, good, plus, and then 1 over x squared we can't do anything with. Right. Again, 3 minus 5 over x we already simplified. Now we should be able to go through and actually take our limit as we approach infinity. Because remember, if we have a square root, one of our shortcuts was, well, yeah, we can just substitute anyway, right? Because that square root is just going to move to the outside of the limit. So this is going to give us the square root. What's the limit as x approaches infinity of 2? 2, good, that's a constant. Plus limit as x approaches infinity of 1 over x squared. That's going to give us a 0 over limit as x approaches infinity of 3. It's going to be 3. And the limit as x approaches infinity of 5 over x. It's another 0. Good, so minus 0. So now when we simplify this, what's this going to give us? Okay, good. The square root of 2 over 3. So there's our limit as x approaches positive infinity. Any questions on calculating that limit now? All right, now we need to look for the limit as x approaches negative infinity, because again, it could be a different limit on the left-hand side now. We'll take the limit as x approaches negative infinity. Same function, square root 2x squared plus 1 over 3x minus 5. All right, first step still the same, right? So we identify what's the degree in the denominator, divide everything by that. So we're still dividing everything by x this time. This first step is still going to be the square root 2x squared plus 1 over x over 3x over x minus 5 over x. All right, now, when we move the x inside, what's it going to become? Good. Now, be careful, right? So when we move it inside, the x itself still is just going to become 2x squared over x squared, just like before, and 1 over x squared, just like before. The difference this time is that we're approaching negative infinity. So that x on the outside now is actually a negative value. So when we move it inside, we have to make sure we account for the negative. So we have to make sure we put a negative on the outside of the square root here. That's the only difference. Okay, so just remember, This x right here, we're approaching negative infinity, so it's a negative value. Just keep the negative on the outside of the square root when we move it inside now. Okay? Any questions about that step? All right, now, denominator is still going to simplify the same way. 3x over x still going to give us 3. And we have our 5 over x. Come down here and finish this out. Simplify the numerator. We have our negative on the outside now. This is going to give us 2 plus 1 over x squared. And then 3 minus 5 over x. Left off my limit. Okay, so now when we go through and we take this limit, what is this going to give us this time? Exactly, right? The only difference now is because we have that negative on the outside of the square root, it's just going to become a negative square root of 2 over 3, right? So we're going to get negative square root of 2 plus 0 over 3 minus 0. And it works out to negative square root of 2 over 3. So again, this is one of those cases where the limit as we approach negative infinity is different from the limit as x approaches positive infinity. It's because of that square root. When we move the x inside, we have to keep the negative on the outside of the square root here. Any questions on that one? All right, now let's make sure we actually answer the question, right? So we were looking for horizontal asymptotes. We're going to have a horizontal asymptote at y equals square root of 2 over 3. We're going to have another horizontal asymptote at negative square root of 2 over 3. All right, now, this is a good place to look at Desmos, check your graph, and make sure that your answers make sense, right? Because let's say that you had forgotten to put the negative on the outside and you only got positive square root of 2 over 3. Hopefully, then the graph would show you, oh, wait, it's not actually approaching that value to the left, right? So let's take a look at the graph. Let's see what it looks like. All right, so we've got square root 2x squared plus 1 over 3x minus 5. Okay, so there's our graph. I'm going to put the asymptotes on here now so we can see if it actually is approaching what we think it should be. So x equals 5/3. That was our vertical asymptote. Okay, so there's the green line. And you can see in this case that we are indeed approaching infinity and negative infinity on either side of that vertical asymptote. So that looks good. Then our horizontal asymptotes, we had y equals square root of 2 over 3. That was to the right-hand side. If I can zoom a little bit so you can see that. Okay, so on the right-hand side there, that purple line, that's our horizontal asymptote. We're approaching from above in this case on the right-hand side, so that looks good. And then again, when you scroll to the left now, notice that the curve is not approaching that same value. So if you had gotten the same value when you did your work, you would say, wait a minute, the graph doesn't justify that, right? It doesn't look right. Okay, but now when we do y equals negative square root of 2 over 3 on the left-hand side, okay, that black line, you can see now that the curve is actually approaching that black line as we go towards the left-hand side now, towards negative infinity. Okay. So again, even though those values are pretty close, right, they are different, and we are approaching different values on the right and the left this time. Any questions on that one now? So again, please use Desmos to your advantage. Graph these functions. because it's a good way to catch any mistakes that you might have made in finding the asymptotes, right? All right. Example 5. Okay, so now we want to find the limit as x approaches infinity of square root of x squared plus 1 minus x. All right. Now, again, we can't just do a direct substitution because infinity is not a number, right? So we can't just say, oh yeah, just plug infinity for x's and see what happens. If you think about what might happen in this case, right, it looks like, well, you know, infinity squared plus 1, and then we're taking the square root, so that's going to basically be an infinity, and then x is basically an infinity. We subtract and they cancel out at 0, right? You can't do that. It doesn't work that way. So what we're going to have to do is try to create some type of function that looks similar to the ones we've been looking at, where we could then think about each of those limits, right? And the only type of limit for infinity and negative infinity that we know how to calculate is when you end up with an x in the denominator. So that's what we want to create, is something where we know what that limit's going to be equal to, okay? So what I'm actually going to do here is I'm going to think about the conjugate of what I've got right here, and I'm going to create a fraction where I have that conjugate on top and bottom. Remember, the conjugate here is just going to be the same thing with a plus instead of a minus. I'm going to multiply by the square root of x squared plus 1 plus x over the same thing, x squared plus 1 plus x. Right? Because that's basically just multiplying by 1, which is completely legal, right? I'm allowed to do that. All right, now we just have to think about what this is going to look like once we do that multiplication. So we've got our limit as x approaches infinity. What's the numerator of that fraction going to look like now? Okay, good, right? So we have the x squared plus 1, because those square roots are going to cancel. And then the outer and inner terms will cancel. That's the whole point of using the conjugate. And then negative x times positive x should give us a minus x to what power? X squared, right? Okay, so there's our numerator. Denominator now is just what we multiplied by. So this is x squared plus 1 plus x. All right, now if we simplify the numerator, then what's that going to leave us with? Just a 1, right? Because the x squares are going to cancel. So we have the limit as x approaches infinity, 1 over the square root of x squared plus 1 plus x. Okay. Now, at this point, we can kind of just reason through what this limit's going to be. So think about this denominator now. I've got some infinite value that I'm, approaching in terms of my x value here. What is that denominator approaching overall then? If I'm substituting extremely large values in for those x values now, what's happening to that denominator? Okay. All right, so the denominator itself is getting what? Larger, right? Okay, because I've got an infinitely large value inside that square root. I'm adding an infinitely large value to it. Okay, so that is getting infinitely large, okay, in terms of the denominator, which means the overall fraction then is going to be getting what? Smaller, right? So what do you think this limit is actually going to be approaching then? 0. Good, right? So it's basically at this point just like our limit as x approaches infinity of 1 over x, right, is equal to 0, okay, because we're still getting that really large value in the denominator. And as we take the limit of 1 over that really large value, we're still approaching 0 the same way we did with 1 over x, okay? But again, you can't just think of it as, oh, well, it's the limit as x approaches infinity of that first piece minus the limit as x approaches infinity of that second piece. You can't do that with infinities because they're not actual numbers, right? So don't try to split up that limit using the subtraction in this case, right? We've got to create that fraction and think about our limit as x approaches infinity of that fraction at that point. Any questions on that one now? All right. Now we want to take the limit as x approaches infinity of sine of 1 over x. All right, so in this case, we've got a composition of functions, right? We've got the 1 over x as the inside function, sine is our outside function, so we're taking the sine of the 1 over x piece. All we really have to do in this case, though, is think about what is that inside actually approaching as x approaches infinity. So what would the inside piece, the 1 over x, be approaching here? 0, right? Because we know the limit as x approaches infinity of 1 over x is going to be 0. So what I'm going to do now is I'm actually going to change this, and we're going to think of this as the limit, use a different variable, as t approaches 0 of sine of t. Okay, so since I know the limit as x approaches infinity of 1 over x is 0, now I can say, well, let's just think of the inside part as t and think about the limit as that t value now approaches 0, since I know what that 1 over x is approaching. Well, if I'm thinking about the limit as t approaches 0 of sine, what would the limit equal in this case? So what would sine be approaching as t approaches 0? 0, right? So from the left and from the right-hand side, right, that's a periodic function, okay, but it's approaching 0 from the left and the right. And so this function right here is going to be approaching 0 now. Another way to think about it, you could actually just say, well, this right here produces sine of 0, right? Because the limit as x approaches infinity of 1 over x is 0, and we know the sine at 0 is equal to 0. Therefore, that overall limit should be equal to 0 also. Because trig functions, we can do direct substitution, so sine of 0 is 0. Any questions on that one now? All right. So now we want to think about the limit as x approaches infinity of sine of x. All right, so in this case, let's just think there's nothing we can really do to simplify sine of x, right? It is what it is. So we're going to have to just kind of think about the graph of this one and what's happening as x approaches positive infinity. So what happens as sine goes towards positive infinity? Okay, tell me this. All right, does sine go to infinity as you approach infinity? So as x goes towards infinity, out towards the right-hand side, does the sine curve go towards infinity? So remember, we're thinking about y values, right? So does the sine curve, in terms of its y values, go towards infinity as you go towards infinity to the right? Right. So as the x value, as x approaches infinity out here, I want to know what's happening to the y value. It doesn't, right? What does it go towards? It goes up and down. It oscillates. Okay, so the highest value it's going to hit is 1, but the lowest value it hits is -1, right? Is it approaching any specific value then as we go out towards positive infinity? No. So what do you think we have to say about this limit as x approaches infinity then? So we can't just call it sine of x. So if we're not approaching a specific value, what do you think we have to say about this limit? Does not exist. Okay, so this one right here does not exist because we're oscillating between two different values, -1 and 1, right? There's no specific value. There's no horizontal asymptote, right? And that's what a limit at infinity would represent. Since we don't have a horizontal asymptote, there's nothing we're approaching. We just have to say that this limit does not exist now. Okay. Any questions on that one? All right. Example 8. We want to find our limit as x approaches infinity and negative infinity for the function x cubed. All right, so again, nothing we can really do to simplify this, right? X cubed is what it is. So think about in this case, as we approach infinity for x to the third power, as I think about infinitely large values in that function, what's happening to the function x cubed in this case? It's getting infinitely bigger, right? So what do you think we could say the limit as x approaches infinity for x cubed is going to give us? Infinity, right? So it is approaching positive infinity in this case, because as I put infinitely larger positive values into x cubed, I'm just getting infinitely larger positive values out, right? So this is just going to give us positive infinity. Any questions on that limit? What about the limit as x approaches negative infinity of x cubed? Good. Because we're raising this to an odd power now, if we're substituting in negative values into this function, it's going to give us infinitely larger negative values, right? So infinitely bigger values in the negative direction. So this is actually going to become negative infinity instead. If you think about your graph of x cubed, it makes sense. Because we know it's the sideways S-shaped curve. It's going to look something like this. So as I go out towards positive infinity on the right-hand side, my y values are approaching positive infinity. And as I go towards x being negative infinity, my y values are also approaching negative infinity that way. Any questions on that one now? So again, a graph with no horizontal asymptotes, right? Because we're not approaching a specific value, but we can at least describe, that the right-hand side is going up towards positive infinity and the left-hand side is going down towards negative infinity now. All right, let's go ahead and take our break right here. Okay, so I've got 11:01. So 11:06, we'll get started back up and finish up this section. All right. So let's take a look here at example 9. We want to find our limit as x approaches infinity of x squared minus x. All right, so again, just like the other one that had that subtraction in it, we can't just direct substitute, right? Because infinity is still not a number. So we can't just say, well, what's the limit as x approaches infinity of x squared, and what's the limit as x approaches infinity of x, and then subtract those values. It doesn't work that way, right? It's not gonna give us the correct answer, actually. In this case, if we do it that way. So what we actually want to do here is anytime you can factor, you're going to want to factor, okay? Because if we can get it down to a product of things, just like if we can get it as a quotient division, then we can actually think about our limits. How could we factor x squared minus x? Good. We have a common factor of x. I'm just going to go ahead and factor that out. So we're going to have limit as x approaches infinity of x times x minus 1. Now we can think about the limit of each one of those factors individually and think about what would then happen if I were to multiply them together. Well, what would our limit as x approaches infinity of x give us? We're just thinking about the limit as x approaches infinity of x. It's going to be positive infinity, right? Because you're thinking about a linear function x with a positive slope. So as you go out towards positive infinity, those y values are getting infinitely larger, right? So that piece by itself is approaching infinity. Now we want to think about the limit as x approaches infinity of x minus 1. What would that limit give us? Also positive infinity, right? Because the only difference between that and x is we've got this linear function now that's shifted down 1 unit, but as we go out towards the right, it's still approaching positive infinity, right, in terms of the y values. This is still going up towards positive infinity. Well, if I multiply two infinitely large values together, two positive infinitely large values, what is that overall limit going to be equal to then? Infinity, right? Okay, so infinitely large value times infinitely large value should give us infinity. So this overall limit now is approaching infinity. Now, again, we could not just do the subtraction piece up front, because if you think about the limit as x approaches infinity of x squared, that's going to be infinity. And if you think about the limit as x approaches infinity of x, that's also going to be infinity. But you can't do infinity minus infinity cancels out and gives you 0. That doesn't work. Okay, so that's why we have to factor. Think about the product of each one of those limits now, since they're both approaching a positive infinitely large value. We know the overall product's also going to go towards positive infinity now. Any questions there? All right. So now we want to find the limit as x approaches infinity of x squared plus x over 3 minus x. So how are we going to do this one? Okay, good. This is a fraction. We can find the degree of the denominator. We can divide every term by that. So what are we going to divide by this time? Just x. Perfect. We have limit x approaches infinity. This time we're going to have x squared over x plus x over x. Denominator is going to be 3 over x minus x over x. All right, now we can simplify. So if we do that, what's our numerator going to give us? Good, right? X squared over x is going to leave us with an x. X over x is 1. Now the denominator 3 over x, we can't do anything with that. And then x over x here is going to give us the minus 1. All right, now let's think about our limits that we've got at this point. So in the numerator, we have an x plus 1. What is that numerator approaching then? Infinity, right? Okay, so just like the last one we looked at where it was an x minus 1, right? That limit of x minus 1 was infinity. Same thing here, linear function, positive slope. That numerator is approaching infinity. Now let's look at the denominator. We can go term by term this time. What's the limit as x approaches infinity of 3 over x? That's going to give us 0. What's the limit as x approaches infinity of 1? That's going to be 1. So we have 0 minus 1 in the denominator. So now when we simplify this, what are we going to get? Negative infinity, right? Because we end up with an infinity over a negative 1. And so this actually simplifies then to negative infinity. So that overall limit of that original function as we approach x, as x approaches positive infinity, the overall limit's actually going towards negative infinity now. So again, be very careful here, right? Make sure that you're still doing the process we always would. Even though the numerator is approaching infinity, the denominator is actually approaching negative 1. So the overall limit now is negative infinity. Any questions on that one? All right. So this will be our last example for this section, and then we'll move on to 3.5. So now it says sketch the graph. So we just basically want to think about all of these limits and things like that that are going to help us to sketch the graph. All right, so we've got x minus 2 to the 4th, x plus 1 to the 3rd, x minus 1. We want to find intercepts and limits as x approaches infinity and negative infinity. That'll give us any horizontal asymptotes. Or at least just tell us what the end behavior is. All right, so let's start with intercepts because this is something we're going to use in section 3.5 also. How would you find x-intercepts for that function? Okay, so good. We're going to set it equal to 0. So we're basically saying 0 equals x minus 2 to the 4th power times x plus 1 to the 3rd power times x minus 1. Okay, so let y be equal to 0. So we're setting the entire function equal to 0 now. Then what would you do to find the x-intercepts? Good. Set each of our factors equal to 0. And it doesn't matter that they're to the 4th power and 3rd power, right? Those are, when we take the 4th root and the 3rd root of 0, it's just going to give us 0 anyway. So we can just say x minus 2 equals 0, x plus 1 equals 0, and x minus 1 equals 0. All right, so what are the x-intercepts going to be this time? Good. So we have x equals positive 2, x equals negative 1, and x equals positive 1. Okay, so anytime you're asked for x-intercepts, set the function equal to 0. If it's already factored, just set each factor equal to 0. If it's not, you might have to do the factoring piece, right? And then you can set each factor equal to 0. Now, how do we find y-intercepts? Okay, good. Plug in 0 for the x value now. So we're looking for the y value when x is equal to 0. So it's going to be 0 minus 2 to the fourth, 0 plus 1 to the third, times 0 minus 1. All right, so if we simplify this now, this is negative 2 to the fourth power. That's going to give us what? Good, positive 16. Then we have 1 to the third power. Well, that's just 1. And then we have 0 minus 1. That's a negative 1. So overall, that y-intercept is going to be what? Negative 16. All right, so anytime it's a function, you can only have one y-intercept. So just keep that in mind. You can never have more than one y-intercept if it's a function. All right, now that we've got our intercepts, now we want to think about those limits. So let's think about our limit as x approaches positive infinity first. Okay. This is x minus 2 to the fourth, x plus 1 to the third, and x minus 1. Well, it's already factored, right? Because remember on the last example, we had to factor first, but this one's already factored. So we can kind of think about each one of these limits as x goes to infinity, and then think about the product of all of that now. So if we look at this first factor, what would the limit as x approaches infinity of x minus 2 to the fourth power give us? It's a positive infinity, right? Because if I put an infinitely large value in there and I raise it to the fourth power, that's just going to give us some infinitely large value in the positive direction. All right, let's do the same thing with the next factor. X plus 1 to the third, if I put infinitely large values into that, what's going to happen to that factor? Also going towards a positive infinitely large value. So that's positive infinity. And then finally, limit as x approaches infinity of x minus 1 is going to be what? Also positive infinity. And if we multiply 3 infinitely large positive values together, that's going to give us what? Infinity, right? So that limit, as we approach positive infinity, should approach positive infinity now. Any questions on calculating that limit? All right, now let's think about our limit as x approaches negative infinity instead. Again, same factors. All right, so go factor by factor here. What's the limit as x approaches negative infinity of x minus 2 to the power? It's going to become positive, right? Because we're raising some infinitely large value in the negative direction to an even power. So that first factor is actually going to give us a positive infinity. Now, the next factor, if we approach negative infinity for x plus 1 to the third, good. Since we're raising a negative infinitely large value to an odd power, that one's actually going to give us a negative infinity instead. And then if we think about the last factor, x minus 1, what's that going to be? It's also going towards negative infinity. And now if we multiply these infinitely large values, 1 positive, 2 negative together, what are we going to get? Good. This is going to work out to a positive infinity this time. So what that tells us about the graph then is on the right-hand side towards positive infinity and the left-hand side towards negative infinity, both of those ends are going up towards positive infinity in the y. Okay. And if you think about this function overall, the degree here would be 4 plus 3 plus an understood 1. So that degree is going to be 8. That's an even degree. Both ends should be going in the same direction. Leading coefficient's positive. That's why they're both going up. And I'm not going to take the time to actually sketch this one out because you could put it in Desmos and see it. But again, right, we have our x-intercepts, we have our y-intercept, we know what the end behavior looks like. We could get a pretty decent sketch of what this graph looks like just based off of that information. Okay. Combine that with what we know about derivatives now for finding mins and maxes, concavity, all that stuff. We can actually get a very accurate graph of what this looks like without needing Desmos at all. So that's where we're headed in section 3.5, is taking information like this with our limits as we go towards infinity and negative infinity, finding any vertical asymptotes, finding all of our intercepts, finding mins and maxes based off what we did in the previous section, thinking about concavity, and then using all of that then to actually sketch some of these graphs. Okay? Any questions here now? All right. Let's take a look at 3.5. All right, so 3.5 is called the summary of curve sketching. So again, like I just said, what we're going to be doing now is taking all this information that we've learned in this unit together and then looking at a specific curve and then thinking about all those pieces. Okay, so each one of these examples is going to take a while, right? We might get through one example in the time we have left at this point. All right, so here's all the things we're going to look for, right? We're going to think about domain, right? Because that's important. Okay, if you have any vertical asymptotes, anything like that, we have to know. If there's any holes in the graph, we need to know that also. And just in general, right, with square roots and things like that, we need to think about what part of the graph we even care about. Then we're going to look for intercepts, which we just did on that previous example, right? X-intercepts, Y-intercepts. So plug in 0 for Y to find your X-intercepts, plug in 0 for X to find your Y-intercept. Then we can think about symmetry, right? And if you remember, we can substitute a negative x into our function to see if we have an even function, an odd function, or if it's trigonometric, right? We can think about any periodicity that it has because that'll help us to sketch it also. Then we can think about asymptotes, okay? So that's both vertical and horizontal. So we have to think about any denominators where it's undefined, think about those vertical asymptotes. Also look at your limits at infinity and negative infinity to find any horizontal asymptotes. At that point, we're going to use our derivatives to find intervals of increase and decrease. And then from that, we can find our max and min values. Then we'll take the second derivative so that we can look at concavity, figure out where it's concave up, where is it concave down, and then if it ever switches, then we know there's points of inflection there. Okay, so these are all the things we're going to look at. That's why I said each one of these examples will take some time. We got a lot of stuff to pick out here, okay? All right, so here's our first curve. We're just going to go bullet point by bullet point here and find each of the pieces we want. So the first piece here is domain. So how are we going to find the domain of this function? All right, good. We need to figure out where the denominator is equal to 0 because we know there's going to be restrictions there. So I'm going to say x squared minus 1 cannot be equal to 0. Now, how would you solve that? Okay, we can add 1, so that'll give us x squared can't be equal to 1. Take your square root, so that's going to give us x cannot be equal to what? Plus or minus 1. Good. So we know in this case, right, there's going to be restrictions on the domain at positive 1 and negative 1. So then if you want to write this in interval notation, we'd have negative infinity to negative 1, negative 1 to positive 1, and positive 1 to infinity. Any questions on finding the domain for that function? All right, part B. Now we're going to look for intercepts. Okay, so let's start with our x-intercept. How are we going to find x-intercepts for this graph? Okay, good. Set the entire function equal to 0. So this is 0 equals 2x squared over x squared minus 1. So let your y value be 0. We're trying to solve for x now. Now, if that fraction is equal to 0, what actually has to be equal to 0 then? The numerator, right? So I can ignore the denominator and just say, well, 0 has to be equal to 2x squared then. Which means x would have to be equal to what? 0, right? If you divide by 2, take the square root, this is still just going to give us x equals 0 once we do that. Right, so that's the only x-intercept that we should have this time. Now let's think about y-intercept. How are we going to find our y-intercept for this one? Go ahead, plug in 0 for your x. We're going to have 2 times 0 squared over 0 squared minus 1. So what's that going to give us? 0, right? So we get 0 in the numerator, negative 1 in the denominator, 0 over negative 1, just going to be y equals 0. If you have an x-intercept at 0, your y-intercept has to be 0 because it has to go through the origin. And remember, there can only be one y-intercept. Okay, so just keep that in mind when you're finding x and y-intercepts. If you already know the x-intercept is 0, you're going to have a y-intercept at 0 in that case. All right, so there's our intercepts. Okay, the next thing we're going to look for is any symmetry that we might have. So how do we say we're going to test for symmetry? Okay, good. Substitute a negative x everywhere we see an x. So we're going to have y equals 2 times negative x squared over negative x squared minus 1. All right, so if we simplify that now, what are we going to get? Okay, good. It's going to give us the same function that we started with because squaring those negatives just gives us 2 positive x squared. And we get a positive x squared minus 1. That means this is an even function since it's the same thing we started with. So what does that tell us in terms of symmetry then? What type of symmetry even functions have? Not x-axis. So remember, a function can never have symmetry about the x-axis because it would no longer be a function, right? Because then it wouldn't pass the vertical line test. So this is going to be symmetric about the y-axis. Good. So just remember, right? It's either even, odd, or neither, right? Those are your three options. Even, symmetry about the y-axis. Odd just means there's symmetry about the origin. Okay, or if you don't get either of those cases, then we just say there's no symmetry at all there. Yeah, the only things that can have x-axis symmetry would be non-functions. All right, any questions about the symmetry here? Yes, so there will be a question on the test where I basically ask you to find all these pieces. I'm probably not going to ask for every single one of them. Most likely it's going to be finding the increasing, decreasing, mins and maxes, concavity, any inflection points. I might also ask for intercepts, right? But you're going to need to know how to go through this process to be able to find all this stuff, right? Because I could ask for any of it on a specific function. Okay. Any other questions here? All right, part D now, we're looking for any asymptotes. So what asymptotes do you want to start with, vertical or horizontal? All right, let's do vertical. How do we find vertical asymptotes? Okay, good. Set the denominator equal to 0. Well, technically, when we found the domain, we've already done that, right? So it's going to be the same as the domain. So this is just going to give us x equals 1 and x equals -1, right? So without doing any further work, since we know we had those restrictions on the domain, that's where those vertical asymptotes are going to be this time. Any questions on the vertical? All right, now how are we going to find horizontal asymptotes? Okay, good. So we're looking at our limit. We'll start with x approaches positive infinity here. And to do that, we are going to have to divide top and bottom by the degree of the denominator, which is x squared this time. So we're going to have 2x squared over x squared minus 1. We're taking the limit as x approaches infinity, 2x squared over x squared over x squared over x squared minus 1 over x squared. So again, anytime you have a rational function like that, look for the highest exponent in the denominator, divide every single term by whatever that is. Now, if we simplify here, we have the limit, x approaches infinity, 2x squared over x squared, the x squares are going to cancel, so that just leaves us with 2 up top. Denominator, x squared over x squared is 1, and then minus 1 over x squared. Okay, so simplifying that now, limit as x approaches infinity of 2 is going to be what? 2. Good. Limit as x approaches infinity of 1, also constant, should be 1, minus limit as x approaches infinity of 1 over x squared is going to be 0. So overall now this is going to be what? Positive 2. Good. 2 over 1, which is 2. Now we do need to consider the limit as x approaches negative infinity, right, just to be sure that it's the same. In this case, right, if we go ahead and we know we're going to divide by x squared, we know we're going to get all this same stuff. So it's going to be 2 over 1 minus 1 over x squared again. And when we take those limits, it's still going to be 2 over 1 minus, what's the limit as x approaches negative infinity of 1 over x squared? Still 0, right? And so this limit is still going to be what? 2. Okay. In general, like I said, for rational functions, okay, your limit from the left and the right here, negative infinity and positive infinity, should be the same. Okay, so you're probably going to get 2 in both cases. But be sure that you're checking both, okay, because again, whenever you have square roots especially, that's when you have to be really careful. So now make sure again that you actually list out the asymptotes. So this time we only have the 1 at y equals 2. All right, any questions up to that point? All right, so let me add a page in here. All right, so the next thing we're going to have to look for are intervals of increase and decrease. So how are we going to find intervals of increase and decrease? We need the derivative, right? So our original function here, I'll write it up here at the top. It'll let me. Y equals 2x squared over x squared minus 1. All right, so how are we going to find our first derivative for that function now? Okay, good. It is a quotient this time, so we're going to have to use quotient rule. So let the numerator be your f, denominator is your g. So we'll say f is 2x squared. G then is going to be x squared minus 1. What is f prime? 4x. Good. And g prime, 2x. Perfect. All right, so then remember, this is going to be g f prime minus f g prime all over g squared. So when we do that, we'll have x squared minus 1 times 4x minus 2x squared times 2x all over x squared minus 1 squared. And this is first derivative y prime. All right, so now if we simplify this, I'm going to go ahead and distribute my 4x here. So that's going to give us 4x cubed minus 4x. And then over here, we can multiply 2x squared times 2x. That's going to give us a minus 4x cubed all over, again, keep this factored, x squared minus 1 all squared. All right, so what are we going to have left in the numerator now if we combine like terms? Just the negative 4x, good, over x squared minus 1 all squared. All right, so there's our first derivative. Now that we have the first derivative, what are we going to do next? Okay, good. We need to set it equal to 0. So we got to find our critical numbers, right? That's the key here. So if we set this equal to 0, remember the numerator would have to equal 0. So it's going to be negative 4x equals 0. But don't forget, we also need to consider where it's undefined for our critical numbers. Okay, so how are we going to find where it's undefined? Okay, good. Look at the denominator, set it equal to 0 also. So x squared minus 1 equals 0. Okay, so again, this is how we're going to find the critical numbers for that derivative. All right, so our first one here, what's our x value going to be for the first critical number? 0. Over here now, if we solve, we're going to get x equals plus or minus 1 when we take that square root. So now when we set up our number line, we have to make sure we use all 3 of those critical numbers. So we make sure we test all the intervals we need to. So I have negative 1, 0, and positive 1. Again, this is our first derivative. All right, so what value do you want to test first? Okay, negative 2 is good. So we'll have negative 4 times negative 2 over negative 2 squared minus 1 all squared. All right, in this case, numerator here is going to give us what type of value? Positive. Denominator is going to give us what type of value? Can we ever get anything other than a positive value in the denominator? No, right? Because we've got an x squared minus 1, right? The only thing we could potentially get there other than a positive is 0, right? We don't want that anyway. We know it's undefined. We're squaring whatever value we get, so it's automatically going to be positive, okay? Just keep that in mind as we're simplifying this. That denominator is always going to be positive. Positive over positive is going to give us what? Positive. Good. So we know that interval is going to be positive. All right, what about the next interval, somewhere between negative 1 and 0? Okay, negative 0.5 is good. So again, we're going to do negative 4 times negative 0.5 over negative 0.5 squared minus 1 all squared. And numerator this time is going to be what? Positive. We said the denominator has to be positive. So overall, this is going to be positive. All right, now we need something on the other side of 0. What can we go with there? Positive 0.5 is good. Now we have negative 4 times 0.5 over 0.5 squared minus 1 all squared. Denominator is definitely positive. Numerator is going to be what this time? Negative. Negative over positive is going to be negative. Good. Then we need something bigger than 1. 2 is good. Negative 4 times 2. Again, I know that's positive. Numerator is going to be what this time? Negative. Negative over a positive is going to be a negative. Good. All right, so then we just need to list out where is this increasing, where is it decreasing, because that's what we're looking for in part E. So what would our intervals of increase be this time? Okay, almost. Be careful. There's a reason that negative 1 is a critical number here. Okay, we have to actually split the interval at that value, because remember, the domain does not include negative 1. Okay, so we can't go through negative 1 because it's not even part of the domain. So we have to say it's from negative infinity to negative 1, and from negative 1 to 0 in this case. There will be an asymptote at negative 1. Then our intervals of decrease are going to be what? Good. 0 to 1 and 1 to infinity. Okay, again, there's going to be that asymptote at positive 1, so that's why we have to split our interval at 1. Any questions on finding the intervals of increase and decrease? All right, now part F is mins and maxes. Okay, so do we have any min or max values based off of what we see here now? Okay, so remember, negative 1 and positive 1 are going to be asymptotes. Okay, and if you look on either side of that, it's increasing at negative 1. It's decreasing at positive 1. Okay, so those aren't going to be mins or maxes anyway. But again, they can't be either because they're going to be asymptotes. So where's the only place we could have a min or a max in this? 0. Do we have a min or a max at 0 this time? Okay. So think about what's happening, right? This interval right here is increasing. This interval right here is decreasing. So if your function goes from increasing to decreasing, what does that tell us? There's a maximum there, right? So we know then that there's going to be a local max at x equals 0. So that's why if you look at your number line, think about those intervals of increase and decrease, and anywhere where it either switches from increasing to decreasing or decreasing to increasing, that's where we're going to have max or min values. Okay? This time it goes from increasing to decreasing, therefore there's a maximum there. Now, how do we find the actual max value at that point? So once we know there's a maximum of 0, we have to plug in 0 to the original function, right? Well, we've technically already done that because that's how we found the y-intercept, right? So if you plug in 0 here, what's our y value going to be? Zero, right? So we're going to have a point at the origin. So the maximum value is y equals 0. So the origin in this case is going to be a local maximum when we actually sketch this graph. Any questions there? All right, now the last piece of this one, and we're going to save it for tomorrow, is to find concavity, right? So how would we find concavity? Good. We need to look at the second derivative, right? And then we're going to think about where that's equal to 0, do our number line test, all that. But again, I don't want to rush through that. We've only got 3 minutes left. So I'm going to save the entire second derivative and concavity for tomorrow. But that's the last piece that we have to do for this one. Okay. But like I said, these do take some time, right, to work through them. So make sure, right, when you're doing your homework, any of the ones where you're listing out all this information, just make sure you're leaving yourself enough time to actually get them done. Okay. All right. Again, don't forget 3.1 to 3.3 homework is due by midnight tonight if you haven't already finished that one. We've already covered all of 3.4 and enough of 3.5, right, that you can actually probably get a good start on that stuff if you want to work on it. Right now, that one's going to be due Thursday. I think that'll probably stick because I think we can probably get through what we need to by tomorrow so that you can have that one done by Thursday night. Again, test is probably going to be posted Monday of next week is what I'm looking at. That will be the very earliest anyway, which means it'll be due sometime in the middle of next week. Okay, so keep all those due dates in mind. Let me know if you've got any questions. Otherwise, have a great afternoon, and I will see you all tomorrow.